It's been a few days since I uploaded a video to my channel, and there's two reasons for that. The first reason is that I've been really studying hard for my analysis test. In fact, I just submitted my paperwork to the math office letting them know that I'm going to take the test in August. So that gives me, it's about halfway through June, so I get a month and a half plus most of August. So I got about 2 months worth of studying to do, which, doesn't feel like very much, but I've studied a lot. In fact, I've accumulated all of my study material here, in case you want to look at it. So the thicker stack on the left is all of my real analysis material. Each sheet of paper represents at least one problem, and I think that there's in the neighborhood of maybe 500 problems here. And you can see the theorems list on the top of all the things that I really need to do. The red dot represents something that I've practiced and memorized, more or less. And then there's just tricks of the trade that show up there. Hopefully everything will play out well for me, but I don't know. Who knows? You really just got to study the notes and just practice a bunch and hope for the best. But that's my real analysis. All fun stuff. And then my complex analysis stuff is over here. I basically, for the last 2 weeks, week and a half, I've been doing nothing but complex analysis because it's the least demanding of the two, because it's the easiest one to prepare for. You have more clarity as to what the problems will look like. So on the channel, actually, I made a video about my study routine, about how I was going to do real analysis a week, complex analysis the next, and then cycle back and forth. I've been kind of sticking to it. But for the last week, it's just I knew that I had to do a bunch of complex analysis. And I didn't really stick to the schedule, but I was still working on problems. This stack has about 300 problems maybe in it, if I had to take a guess. It's not as thick as this one, but there's still a lot in here. And you can see the list of theorems on the top. Yeah. Symmetry principle. I have tricks about how to memorize some of these theorems. There's Rouché's theorem. Famous Rouchet. But anyway, I've been studying for this hard, and probably the biggest reason of why I've been studying for it, in addition to not making videos, is because I still have this complex analysis practice qualifying exam that has been sitting on my desk for like the last 6 months. It was stapled, so it was to deter peeking. But a couple days ago, I studied my butt off this so hard so that I could take this test. So I took it a couple days ago, finally broke the seal. And I took it at 1 o'clock in the morning, and I finished at about 4:30, which is about 3.5 hours of complex analysis. Overall, it went better than the real analysis test. And I don't really know why it doesn't take me as long to study complex as real, despite having much more practice with real than complex, which is either a good sign or a bad sign. Good sign is that I understand the material. Bad sign is I really don't understand the material, and I have a false sense of security in my abilities. Anyway, so the bulk of this, or the reason I'm making this video is because I want to show you inside this packet. So let's look at part 2 of the real analysis test that I took back in January. All right, so let's look at this test. Part 1. The first question is always about proving a theorem from class. So this is a lemma that was used in the proof of the Riemann mapping theorem. If omega is an open set and Fn is a sequence of analytic functions mapping from omega to C, they are 1-to-1, and they converge uniformly to F on any compact subset of omega. Prove either that F is 1-to-1 or F is constant. Okay. So my first thoughts when I saw number 1, when I cracked open this test, was, oh crap, it's the Riemann mapping theorem. Because the Riemann mapping theorem takes a while to prove, which is why he only chose the lemma instead of the whole thing. And overall, my reaction toward the lemma was a bit disappointing because I was disappointed. The reason I was disappointed is because I don't like... Well, I was preparing for famous theorems that have small tricks to them, like Cauchy-Goursat theorem or Max Modulus principle, Louisville's theorem, yada yada yada, Schwartz lemma, that's another one. So I practiced those a lot. And when I saw this, it made me realize, like, I really do have to study every single lemma and theorem that he gave me, because I didn't really look at the Riemann mapping theorem too much because of how long it was. So when I see this, I'm like, well, it looks like I have to put in the effort and quit cutting corners and actually study everything, which kind of disappoints me. But the proof is not too difficult. In fact, I'll show it to you at the end of the video. Alright, so question number 2. Find a conformal map between the following shape and the upper half plane. Question 2 was the easiest one on this test because this problem was given to us as a homework problem, but it was slightly modified. In fact, the only difference is that this shape was turned upside down. So he gave this to us as a homework problem, and I remember doing it at the board, and I got credit for it. So I essentially just repeated the argument, just flipped it upside down first, and then just repeated that argument. So number 2 is the easiest one on this test, in my opinion. Number 3, does there exist a closed curve gamma in the complex plane that does not pass through 0 and 2, such that the following integral is equal to 2 pi I over 3? If yes, give an example. If no, explain why. Number 3 is the automatic contour integral problem. Like, they always give you a theorem, conformal map, contour integral, and then 4 and 5 are, you know, dealer's choice. So I knew what to expect with 1, 2, and 3. Number 3, I don't like how he asks, does there exist a curve, rather than just, you know, calculate an integral. But this problem wasn't that difficult, in my opinion, because usually when they ask, does something exist, a lot of the time it doesn't exist, and you have to explain why. And there's usually some sort of little trick that you can do. And I'm not going to show you my answers to these problems because it hasn't been graded yet. But I believe the way that this problem is solved is that you use residue theory for the poles at 0 and 2. And then you look at how that relates to 1/3, and you'll get some sort of contradiction. So you suppose that such gamma exists. You have to figure out how many times it can loop around 0 and 2, and in what direction it can loop around 0 and 2, because the orientation matters. But essentially what I get is that 4 is equal to 3 times an integer, is what I got in the end, and that doesn't make any sense. So that was my contradiction. So 1, 2, and 3. So 2 and 3 really just took me about an hour to write up. Number 1, if you know it, you can just write it up in 5 minutes. But 2 and 3, just to make sure I didn't screw anything up, took me about an hour to do these two. And I don't really have any complaints about 2 and 3. Number 1, I'm a little bit salty that I have to study every single theorem now, rather than just like the super name recognizable theorems. But the theorem itself isn't that bad. 4 and 5 are the ones that scared me the most because I didn't really know what to expect with them. So number 4 says that f and g are 2 analytic functions in the disk of radius 2 centered at the origin, such that g is not identically equal to 0. Show that f of z plus z to the n times gz has at least one root for all sufficiently large n. Okay. So when I read number 4, the first thing that comes to mind is Richet's theorem. So Richet's theorem is all about comparing the size and modulus of functions. And essentially what I want to say here is that I noticed that Zn Gz has a root at 0. So we know it has at least one root, a root at 0. And I want to show that this function, for sufficiently large n, has greater modulus than this function. And then I can apply Richet's theorem to say that this sum has one root, at least one root. The trick is figuring out how to get the conditions for Rouché's theorem in the first place. And I used Taylor series expansion at 0 and compared coefficients, and after about an hour and a half of thinking about it, I think I wrote down something that makes sense. So I'm curious as to what kind of score I get for number 4. But at least with number 4, I knew the approach, I think, of what to do. That I needed Rouché's theorem, because Rouché's theorem is all about counting roots. Number 5, I don't really know how to make my feelings about it. You have an abounded open set omega. It's not necessarily simply connected. It contains the origin, and f is an analytic map from omega to itself, such that f of 0 is equal to 0. And we want to prove that the modulus of f prime of 0 is bounded above by 1. And then he supplies us with a hint, and he just says iterate. The reason I have mixed emotions about this problem is because when I read this problem, my mind immediately went to Schwarz lemma and Schwarz-Pick theorem, because it just smells like it, you know. You have a bounded open set, which means that I have a bounded open set that's simply connected, I believe, a neighborhood at 0, because it's open, right? Because open sets are essentially made up of small disks at the end of the day, if I remember my topology correctly. And so essentially what I did was I drew a tiny circle about 0 and said that conformally it's equivalent to the unit disk, which sets me up for Schwarz-Pick and Schwarz lemma. So given all of this, I essentially, once I set up Schwarz-Pick lemma, I said, okay, now apply it to this guy, which can be got immediately from it. But that's only if my conformal mapping argument made sense. I may be completely wrong on it, but I could have sworn that I've done a homework problem where I did that, where I had some weird open set, and I didn't construct the conformal map, I just used the Riemann mapping theorem to say we have a disk at the origin that is conformally equivalent to the unit disk, and then I proved some property about an analytic function, and he said that that was a legitimate way of doing it. So I essentially just used that same kind of argument to say, okay, we have a disk at the origin, we can pretend that it's the unit disk, and then use the Schwarz-Pick theorem. The problem is that his hint says to iterate, and I'm not entirely sure what he's getting at there, which leads me to believe that my intuition was wrong for 5 and I completely botched it. But let me know what you think of these 5 problems. In all things considered, I thought that this test was much more fair, I guess. I don't know about fair. I liked it more than the real analysis test. Let me put it that way. I thought that it was a good batch of problems, good PhD problems. The only thing I would complain about is maybe the theorem, but that's just me being a crying toddler. He's like, why didn't you pick Cauchy-Goursat? I practiced that. But no. They said, okay, here's a part from the Riemann mapping theorem. It's like, I don't want to do Riemann mapping theorem. But anyway, that's what I thought of this test. I didn't think it was too hateful. I thought it was fair. I thought this was a fair test. So as promised, I will show you the proof of number 1. I actually wrote it up earlier, but instead of showing you the one that I wrote up earlier, I'm just going to show you the one that I wrote and submitted. Or yet to submit. I haven't submitted it yet, but everything here is as is. I'm not going to change anything. So the way you do it is you proceed by contradiction. You suppose f is not a one-to-one function, which means that there exist 2 points in omega, z1 and z2, where z1 and z2 are not equal, but f of z1 is equal to f of z2. So that's just the definition of one-to-one. And then you let gn be equal to fn minus fn z1. And we make the observation that gn has a 0 at z1, but also it is the only 0 at z1, because fn is assumed to be one-to-one. We only assume that f is not one-to-one. We don't say anything about fn, other than it's analytic and one-to-one. So gn has to be well, okay, so the only thing we can... Okay, so at the moment we just know that the only root of Gn is Z1. Okay, we have uniform convergence. Gn uniformly converges to G, and G is defined in a similar manner on any compact set. So, okay, so then I make that comment here. Now you need to use some residue theory. You make an integral, G prime over G, function of zeta, 1 over 2 pi I, and we are integrating over a circle of radius r centered at Z2, and you want to make it small enough so that Z2 is inside the circle. So I probably should have made a mention here. I should have mentioned here that Z1 is not inside the circle, so I needed to clarify that here, so that's a mistake. I'm not going to fix it because it'll make the test less legitimate if I do that. Okay, so how do you finish? Because we have uniform convergence of Fn to F, we know that 1 over Gn converges uniformly to 1 over G on the circle, and the same thing with the derivatives on the circle, which means that we can pass the limit inside the integral, and we have that this integral converges to this integral, or this sequence of numbers converges to this sequence of numbers. I keep screwing up. This sequence converges to this number. That's all I want to say. But this value over here is all zeros because Gn zeta, remember, we're interested in the singularities of the function inside, which means we're interested in the roots of Gn. But Gn only has roots at Z1. And the circle is small enough to where Z1 is not inside, which means that we have a bunch of zeros here. But this integral is equal to 1. So how can a sequence of zeros converge to 1? And that's essentially the contradiction, and you're pretty much done. At least this is the proof that's presented in the Stein-Cecarci book, which I used to study for this. So that's the theorem. I hopefully did not screw too much up. He'll ding me on this part here, which in that case he'll give me like 8 out of 10 just because I didn't say Z1 wasn't inside. Although maybe since I set it down here he'd be fine, but because it's not in the right order, he'll ding me on it. But I don't know. Let me know what you think of this test. I thought it was pretty fair and interested in seeing how the one in August will go.